The quest for habitable planets beyond our own has long fascinated astronomers and researchers alike. But what was once relegated strictly to the world of science fiction is quickly become a reality. Still, the chances of finding a true second Earth are very slim. This is because our home not only boasts the perfect conditions for supporting life, but we, having developed here, are perfectly adapted to the characteristics of our little blue rock. But eventually, through time or human activity, our world might become less and less habitable for us, and we might in fact need a new place to call home. So, where might we go and settle next? Before we can explore what other planets might be habitable for humans, we must first understand what makes Earth habitable in the first place. After all, in a near-endless sea of planets covered by molten rocks, gaseous clouds, and stormy sands, Earth so far stands alone. The biggest factor in all of this is water. After all, water is essential for life as we know it, and Earth's unique position in the solar system and moderate temperature range allows for the existence of liquid water on its surface. While we may take this for granted, only a handful of planets have been found to boast this critical substance. The other essential factor in Earth's habitability is our atmosphere. Earth's atmosphere consists primarily of nitrogen and oxygen, which provide the necessary gases for respiration and protection from harmful solar radiation. It also helps influence what is, for now, a relatively stable climate, with a moderate range of temperatures and minimal environmental extremes. This temperature regulation is further aided by a variety of major geological processes. Last but not least, Earth possesses a strong magnetic field that shields it from harmful solar and cosmic radiation that might otherwise eradicate life in a very short amount of time. The next thing we need to understand when considering what makes planets habitable is their position within their solar systems. The vast majority of planets, being smaller celestial bodies, are locked to the gravitational pull of a star. Their proximity to this star, and the type of star it is, sometimes makes all the difference between a potentially habitable planet, a frozen block of ice, and a scorched ball of flaming rock. This simple fact has led scientists to come up with a sort of litmus test for evaluating a planet's habitable potential. Specifically, they've learned to search for planets located within the habitable zone, also referred to as the Goldilocks Zone, where conditions are just right to support life. Such planets typically have temperatures suitable for liquid water to exist on their surface. They are also most likely to have an atmosphere that can protect any life that exists or immigrates there from harsh solar rays. But there's more to it than that. Indeed, colder and fainter stars, such as red dwarfs, tend to have a larger habitable zone compared to hotter and brighter stars like our Sun. In these instances, there is a lot more room for error in defining what planets could prove survivable to humans. In order to more easily refine their searches, astronomers classify exoplanets according to two scales. The first is the Comparative Habitability Index, which ranges from 0 to 1. By this measurement, a 0.34 planet would mean certain death for human colonizers, and 0.75 and above would require adaptation, but not be entirely impossible. The other scale is the Earth Similarity Index, which ranges from 0 to 1 as well. A 0.25 would be more akin to Pluto than Earth, and a 0.99 would have all the comforts of our planet save a few small differences. Theories regarding exoplanets have existed for hundreds of years, but their discovery is actually quite recent. In fact, as of the last count, there are over 5,300 known exoplanets in total. And thanks to improved technology such as the James Webb Telescope, this number continues to grow at a rapid pace. Initially, many of the exoplanets discovered were gas giants, similar to Jupiter and Saturn. This was mainly due to technological limitations, which meant scientists could mostly only see the largest celestial bodies. However, recent advancements in technology and observation techniques have allowed scientists to identify Earth-like exoplanets with conditions more closely resembling our home planet. In the 19th century, astronomers began to study variations in the brightness of certain stars, known as stellar variability. This led to the discovery of binary star systems, where two stars orbit around a common center of mass. While this didn't directly detect exoplanets, it hinted at the possibility of multiple objects in star systems. By the mid-20th century, astronomers began attempting to directly image exoplanets using ground-based telescopes. Limited by atmospheric interference and the difficulty of distinguishing planets from the glare of their parent stars, these early efforts yielded no conclusive results. Later, astronomers Michel Mayor and Didier Queloz pioneered the radial velocity method, also known as the Doppler spectroscopy technique. This method detects exoplanets by observing the subtle back-and-forth wobble in a star's motion, caused by the gravitational pull of an orbiting planet. Finally, in 1995, the team made the groundbreaking discovery of 51 Pegasi b, the first confirmed exoplanet around a sun-like star. Perhaps the biggest leap forward in the search for exoplanets came in 2009, when NASA launched its Kepler Space Telescope, a device created with the primary goal of Earth-like exoplanets. Throughout its mission, Kepler detected thousands of examples, revolutionizing our understanding of exoplanetary demographics and diversity. The James Webb Space Telescope recently provided us with valuable information on K218b, an exoplanet first discovered back in 2015. K218b sits around 124 light-years away from Earth in the Leo constellation. The star, K218, is classified as an M-dwarf and is both cooler and smaller than the Sun. K218b orbits the star at a lightning pace, just 33 days. However, it is far larger than Earth, roughly 8.63 times in fact. K218b is located within its star's habitable zone, with temperatures suitable for liquid water to exist. However, whether it is habitable depends on a variety of different factors, some of which we're just now starting to find answers to. Recent observations by the James Webb Space Telescope have revealed the presence of methane, carbon dioxide, and possibly dimethyl sulfide in the planet's atmosphere, with DMS being a potential biosignature. This seems to suggest that K218b might be a Hycean exoplanet, or one that has the potential to possess a hydrogen-rich atmosphere and a water-ocean-covered surface. In just one pass, the James Webb Telescope provided us with more information than 8 years of research. As it continues to explore our cosmos, no doubt it will show us and tell us a whole lot more about our current place in the universe and where we might go next. Twin Earths is a term used in the context of exoplanet research to refer to planets that closely resemble Earth in various key aspects. Generally, these would be over 0.85 on the comparative habitability and Earth similarity indices. Such exoplanets are perhaps the best option for expanding our influence outside of our solar system. And while we've yet to find anything that could truly be defined as a twin for our planet, that does not mean no such planets exist. It's also worth noting that our ability to evaluate planets that are sometimes millions of light-years away is less than perfect, not to mention the fact that it would take centuries to properly catalog each one. For that reason, astronomers have come up with yet another set of criteria that allows them to quickly evaluate the potential of a given planet before moving on. As previously mentioned, scientists tend to seek out exoplanets that are similar in size to Earth. This is important because Earth's size corresponds to a rocky, terrestrial composition rather than a gas giant like Jupiter. A rocky surface is crucial because it provides a stable platform for geological processes and the potential for liquid water. Rocky surfaces also allow for the formation of continents, oceans, and climate cycles that can influence the availability of nutrients. Twin Earths would most likely orbit a star that is similar in size and radiation output to our own Sun. This ensures that the planet receives an appropriate amount of energy for conditions conducive to life. Stars that are too massive or too dim can lead to extreme temperatures, making habitability less likely. And while a Goldilocks Zone orbit is essential, the orbit must also be relatively stable. This is because any extreme variations in a planet's orbit can lead to erratic and inhospitable climate changes. Imagine traveling 1,000,000 light-years and setting up an entire civilization only to find out that a planet experiences 500 years of darkness every 2 centuries. There are just a few of the dozens of variables astronomers need to consider just to begin evaluating a potential second Earth. Fortunately, thanks largely to Kepler and the James Webb Telescope, we already have some contenders. This is GLIESE 667, a triple star system positioned approximately 23 light-years away from Earth within the Scorpius constellation. For reference, a light year refers to the distance that light travels in one Earth year. It is equal to about 5.88 trillion miles, or approximately 9.46 trillion kilometers. This is the universal measurement by which time and distance are evaluated in space, and it factors significantly in our potential to move from planet to planet. In the context of exoplanets, GLIESE 667 represents an exciting discovery, as it was the first instance where a low-mass star system was found to host several potentially habitable planets. Within this intriguing system, all three stars boast a lower mass and luminosity than our Sun. The smallest star, GLIESE 667c, is classified as an M-type red dwarf. It is around 33% of our Sun's mass and is, by comparison, rather faint and cold. However, these unique properties may be precisely the key to unlocking habitable opportunities within the system. You see, GLIESE 667c boasts half a dozen planets at least, and, depending on who you ask, 3 or 4 of them could be classified as super-Earths. This is a term used to refer to exoplanets larger than Earth, but considerably smaller than gas giants. Among these intriguing super-Earths, GLIESE 667cc stands out as a particularly fascinating candidate. This exoplanet is approximately 3.8 times the mass of Earth and has a radius 1.8 times that of our home planet. It occupies the second position in distance from its host star and has a remarkably short orbital period of just 28 Earth days. With an Earth similarity index of 0.85, it has been dubbed the Holy Grail of extrasolar planets. However, there are challenges to consider, as GLIESE 667cc is tidally locked due to its close proximity to the star. This means it takes the same amount of time to spin once about its axis as it does to orbit once about its parent star. As with our Moon, this results in eternal day on one side and perpetual night on the other. Astronomers theorize this most likely creates extreme temperature variations, which could have huge implications for the planet's climate. Another factor to consider is the general instability of GLIESE 667cc's star. These types of red dwarfs are known for radiation flares, some of which are powerful enough to eradicate all life on a planet that lacks a sufficient atmosphere. Finally, due to its size, living on GLIESE 667cc would require a great deal more effort than living on Earth. Estimates put the gravitational strength at around 60% higher than our own. So if you weighed 200 pounds on Earth, you'd step onto GLIESE 667cc to find that you weighed 320 pounds instead. GLIESE 667cc's siblings, GLIESE 667ce and GLIESE 667cf, also offer potentially habitable zones, although they are farther from the star. This means that depending on what sort of atmosphere they have, they might be too cold for human life. However, if the theories about the star's powerful radiation flares are true, living on GLIESE 667ce or GLIESE 667cf could offer some valuable protection. It's unlikely we'll find out anytime soon, though. With our current technology, it would take us 850,000 years to get there. The discovery of Kepler 452b in 2015 marked a significant milestone in exoplanetary exploration. Indeed, it represented the first Earth-like planet found orbiting a star similar to our Sun, making it a promising candidate for human habitation. Its nickname, Earth-2, was largely due to its host star, Kepler 452, which shares several characteristics with our Sun. For instance, both are G-type stars, which are known throughout the galaxy to be relatively stable and provide a suitable environment for potentially habitable planets. Kepler 452b, the exoplanet in question, has a size roughly 1.6 times that of Earth. Despite its star being brighter and larger than the Sun, Kepler 452b only receives about 10% more solar energy than Earth. Though we don't have a large amount of information about Kepler 452b, astronomers are pretty sure it has a rocky surface. This would increase the likelihood of several factors crucial to the development of life. Of course, scientists wouldn't even be considering the planet if it didn't reside within the star's habitat zone, which it does. In fact, it's been orbiting within this zone for more than 6 billion years, which means Kepler 452b may have had a substantial head start in the development of life. Kepler 452b's orbital characteristics are also intriguingly Earth-like, as it orbits its star in a manner reminiscent of our own planet. If we were to migrate there, no doubt things would seem quite familiar. For instance, the levels of sunlight and surface temperatures on Kepler 452b are believed to be comparable to those on Earth, creating conditions conducive to plant growth and supporting a potentially diverse ecosystem. Scientists speculate that the exoplanet possesses water, a robust atmosphere, and even volcanoes. In fact, there's even evidence to suggest that Kepler 452b's carbon dioxide concentrations are similar to those on Earth, which is yet another key factor in habitability. However, Kepler 452b's larger size results in a stronger surface gravity, effectively doubling the weight of its inhabitants. Over time, with evolution and adaptation, life forms could potentially adjust to this gravitational difference. However, it would be extremely debilitating at first. Fortunately, we'll have plenty of time to prepare, because the Kepler 452 system is a full 1,800 light-years away. The soonest we could arrive would be in 2.8 million years, 14 times as long as human beings have been alive on our current planet. Another Earth-like planet scientists and astronomers continue to closely evaluate is Kepler 186f. Situated approximately 500 light-years away within the Cygnus constellation, Kepler 186f orbits around Kepler 186, a red dwarf star. As with the other exoplanets on this list, it too falls within the habitable zone. However, unlike the other, Kepler 186f is very close in size to Earth, just 10% larger. This reduces the chances that we'd be forced to endure heavy gravitational changes were our species to immigrate here. Like Earth, the planet also has a very stable axial tilt, which would result in regular seasons and contribute to a relatively consistent climate. However, there are major differences between the two planets as well. For starters, Kepler 186f completes an orbit around its star in approximately 130 days, which means New Year's Eve would be a far more frequent celebration. And because it is positioned at the outer boundary of its star's habitable zone, it receives only about a third of the heat energy that Earth gets from the Sun. As a result, its conditions may more closely resemble those of Mars than Earth. One significant challenge in assessing Kepler 186f's potential habitability is our limited knowledge of its atmosphere. Without a clear understanding of its atmospheric composition, it is difficult to determine whether water exists on the planet's surface or if it could support life as we know it. And thanks to its 500 light-year distance, reaching Kepler 186f would be a monumental feat, taking an astonishing 780,000 years with current technology. It's likely that human beings would need to develop light-speed travel if we were to ever move our entire civilization to a new planet. Still, the fact that that hasn't happened yet is no reason for scientists to stop looking for new potential homes. And that's it for the video. Thanks for watching, and subscribe for more videos.